Preparing for an AI reliability engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How is reliability different for AI systems compared with traditional software services? AI reliability extends SRE by treating models, data, and prompts as production dependencies. I still care about uptime, latency, and error rates, but I also track prediction quality, hallucination risk, data drift, safety violations, and feedback loops. A reliable AI service needs versioned models, reproducible datasets, robust fallbacks, evaluation gates, and incident playbooks. The key shift is that failures can be statistically wrong, not just technically down. While answering, focus on how AI reliability expands SRE beyond uptime into data quality, model behavior, statistical failures, safety, observability, evaluation, and rollback practices in production. Question 2. How would you define SLOs for a production LLM-based assistant? First, I separate service SLOs from quality SLOs. For an LLM assistant, service SLOs might be 99.9% availability, P95 latency under 2 seconds, and bounded error rates. Quality SLOs could track grounded answer rate, policy violation rate, user escalation rate, and regression against golden evaluations. I avoid vague accuracy targets and define measurable user outcomes. Then alerts fire only when customer impact or safety risk crosses a threshold. Make sure to cover service-level objectives for latency and availability, plus model quality SLOs such as groundedness, safety violations, escalation rate, regression thresholds, and alerting based on user impact. Question 3. How do you detect and respond to data drift in an AI system? Data drift is a mismatch between the training distribution and current production traffic. I monitor feature distributions, missing values, label delay, embedding shifts, and prediction confidence. For detection, I use statistical tests, population stability index, slice-based metrics, and business outcome checks. Drift alone is not always an incident. I correlate it with quality degradation before retraining, rollback, or traffic throttling. The best systems combine automated alerts with human review. In your answer, talk about training serving skew, feature distribution changes, label delay, embedding drift, slice-based monitoring, statistical tests, business outcome correlation, and when drift should trigger retraining. Question 4. What approaches would you use to reduce hallucinations in a generative AI product? Hallucination control starts by constraining what the model is allowed to say. I use retrieval-augmented generation with trusted sources, citation requirements, confidence thresholds, and refusal behavior when evidence is missing. I also add prompt rules, output validators, factuality evals, and post-generation checks for risky domains. In production, I monitor unsupported claims and user corrections. The trade-off is coverage versus safety. Sometimes the reliable answer is, I don't know. Be sure to mention retrieval grounding, citations, confidence thresholds, refusal behavior, factuality checks, output validators, monitoring unsupported claims, and the safety versus coverage trade-off for LLM products. Question 5. How would you safely roll out a new model version to production? A safe model rollout is progressive, measurable, and reversible. I start with offline evaluation against golden sets and adversarial cases, then shadow traffic to compare outputs without user impact. Next, I canary a small percentage by segment, watching latency, cost, error rate, safety violations, and quality metrics. If regressions appear, rollback should be automatic or one click. I also keep model, prompt, and feature versions tied to every decision. While answering, describe offline evaluation, shadow traffic, canary rollout, model and prompt versioning, quality metrics, safety metrics, rollback plans, and segment-level monitoring before full deployment. Question 6. A deployed recommendation model suddenly starts producing harmful recommendations. What do you do? If recommendations suddenly become harmful, I treat it like a production incident with an AI-specific lens. First, I contain impact, disable the model, route to fallback rules, or reduce traffic. Then I inspect recent model, prompt, feature, data, and dependency changes. I quantify affected users and slices, preserve logs, and communicate clearly. After recovery, I write a blameless postmortem with new evals, monitors, and release gates to prevent recurrence. Make sure to cover containment first, fallback activation, change investigation, affected user quantification, data and prompt inspection, communications, blameless postmortems, and prevention through new monitors and tests. Question 7. What observability signals are most important for AI reliability? AI observability should connect infrastructure signals with model behavior. I collect request latency, token usage, GPU utilization, timeout rates, provider errors, input features, prompts, retrieved documents, model versions, confidence, and output categories. I also track slice metrics by region, language, customer type, and sensitive cohorts where appropriate. Raw logs need privacy controls and retention limits. The goal is fast debugging. Given a bad answer, I can trace why it happened. In your answer, include infrastructure metrics, model inputs and outputs, token usage, retrieved context, confidence, slice metrics, privacy controls, traceability, and debugging workflows for bad predictions. Question 8. How do you design fallback and degraded mode behavior for AI services? Degraded mode keeps the product useful when the AI layer is slow, unsafe, or unavailable. I design fallbacks such as cached responses, rules-based recommendations, smaller local models, retrieval-only answers, or human escalation. The fallback should be explicit to users when quality changes. I test it regularly, not only during outages. Reliability improves when the system fails closed for safety and fails soft for convenience features. Be sure to mention graceful degradation, cached responses, rules-based fallback, smaller models, retrieval-only mode, human escalation, user transparency, regular fallback testing, and fail-closed behavior for safety. Question 9. How would you protect an AI agent from prompt injection and unsafe tool use? Prompt injection is an attempt to make the model ignore developer instructions or leak data. I defend with layered controls, separate system instructions from user content, sanitize retrieved text, restrict tool permissions, validate tool arguments, and enforce server-side authorization. I never rely on prompting alone for security. I also red team with malicious documents and jailbreak prompts. The principle is least privilege. The model can suggest actions, but trusted code enforces them. While answering, focus on prompt injection as a security problem, not just a prompt problem. Include tool permissions, authorization, input sanitization, retrieved content isolation, red teaming, and least privilege. Question 10. What should an evaluation pipeline for a production AI system include? An effective evaluation pipeline has layers. Offline, I run curated golden sets, adversarial tests, regression suites, and slice analysis before release. Online, I measure user success, complaint rate, escalations, and human review outcomes. For LLMs, I combine exact checks, semantic similarity, rubric-based graders, and calibrated human audits. I watch for evaluator bias and version the eval data. A model only ships when it beats baseline on predefined gates. Make sure to cover offline regression suites, golden datasets, adversarial cases, online outcome metrics, human review, semantic and rubric-based evaluation, evaluator bias, versioning, and release gates. Question 11. Why is reproducibility important in AI reliability, and how do you achieve it? Reproducibility means I can explain and recreate a production prediction later. I version training data snapshots, feature code, prompts, retrieval indexes, model weights, hyperparameters, containers, and serving configs. Each inference log should include correlation IDs and artifact versions, while respecting privacy. This matters for debugging, audits, rollback, and compliance. Without lineage, teams guess during incidents. With lineage, they compare exact inputs and outputs across releases. In your answer, talk about artifact lineage across data, features, prompts, retrieval indexes, weights, containers, configs, inference logs, privacy constraints, audits, rollbacks, and exact production replay. Question 12. How do you manage latency and cost reliability for LLM inference? For LLM inference, reliability includes predictable latency and cost, not just correctness. I reduce tail latency with streaming, request timeouts, batching, caching, prompt trimming, smaller models, and regional routing. I manage cost using token budgets, model tiers, rate limits, and workload prioritization. I also track provider quotas and failover options. The trade-off is quality versus speed. Premium models should be reserved for cases where they materially improve outcomes. Be sure to mention tail latency, streaming, batching, caching, prompt trimming, smaller model tiers, token budgets, rate limits, provider quotas, failover, and quality speed trade-offs clearly. Question 13. What data quality checks would you put in place before model training and serving? Bad data creates bad model behavior, even when infrastructure is healthy. I put quality checks at ingestion, feature generation, and training time. Schema validation, range checks, freshness, uniqueness, leakage detection, and label quality sampling. For streaming systems, I alert on missing partitions and delayed events. I also maintain data contracts with upstream teams. When a check fails, pipelines should quarantine data rather than silently poisoning production models. While answering, cover schema validation, freshness, range checks, uniqueness, leakage detection, label quality, streaming partition delays, data contracts, quarantine workflows, and preventing silent production poisoning. Question 14. When would you use human-in-the-loop review in an AI reliability strategy? Human-in-the-loop reliability is about using people where automation is uncertain or high risk. I define escalation triggers based on confidence, policy category, customer tier, or potential harm. Reviewers need clear rubrics, tooling, and feedback paths into datasets and evaluations. I also measure reviewer agreement and turnaround time. The goal is not manual patching forever. It is safer operation while the model and controls improve over time. Make sure to cover uncertainty-based escalation, risk categories, reviewer rubrics, feedback loops into training and evaluation data, reviewer agreement, turnaround time, and avoiding permanent manual dependency. Question 15. How would you plan capacity and failure handling for a GPU-backed AI service? Capacity planning for AI services must model compute bottlenecks, traffic bursts, and dependency limits. I forecast QPS, token volume, context length, GPU memory, batch size, and cold start behavior. I use auto-scaling with warm pools, queue back pressure, admission control, and priority classes. I test node failures and provider outages through game days. The important point is graceful shedding. Protect critical requests instead of letting overload break every user. In your answer, include QPS, token volume, context length, GPU memory, batching, auto-scaling, warm pools, back pressure, admission control, priority queues, failure testing, and graceful load shedding. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.